one. So this little wheel problem, right, with the mass again elevating and this one descending, we have choices on how to deal with it. We could deal with it through torques and forces or energy. Now, I'll remind you that they might actually ask you for a very specific method. It kind of does right now, doesn't it? Look, does it leave you freedom? No, it says go with forces by necessity. So it's okay, we'll obey that. Otherwise, we'll get 0, okay? So Jamie, and I think Rahimad should be good now to hear. We're also recording, so you can rewatch at your own leisure. Give me some forces that are acting, let's say on M1 right now.
Tension and gravity.
What about the other mass?
Same thing. But
okay.
And gravity, yeah.
And gravity. And what about on the pulley?
The 2 different tensions.
We have 2 tensions. They are the reaction forces to the ones that are acting on the boxes. Which one is bigger? If I was to judge right now, which tension here is bigger, Jamie? On which side?
The right side.
The right side, because we're spinning clockwise. So really, this is the bigger vector here. Okay. These actually are equal, obviously. And this mass here is, of course, bigger than everybody because it's going to drive the whole system down. So he needs to be bigger than T2. Not that this matters really right now for you, but it's nice to have a physical understanding that T2 is greater than T1 and that M2G is greater than T2. It's good to have this physical understanding. We don't need those though. Okay, so we've labeled our conversion table. We have every relationship we want ready to go. I'm gonna assign here to Julie now. Okay, so Julie, we're gonna be working on this guy. What can I set as a positive direction?
You can set up.
And that's because again, we have that lined up with our acceleration, right?
Mm-hmm.
Let me just open here one sec. Let me just open the room. So if Rahimah needs to reconnect, she can just reconnect immediately. There we go. Okay, so we have up as the positive. Let me move us a little bit further from the page. Okay, we can call that plus y. It really doesn't matter. So here's our F net y. Newton's second law says that this should be equal to what?
Mass times acceleration.
Do we have an acceleration right now in the y direction?
No.
Yeah.
Right?
That's what we labeled the y direction because of, right? We assigned y here to go up because our acceleration is going up. So we actually do have one. So whose mass are you putting in here and what acceleration are you putting there?
Mass 1 and acceleration 1.
Good. And then for this, what's happening in the y direction right now? For mass 1, we're focusing on mass 1.
It's going up.
Which of these forces is positive? Which one?
The T1 is positive. The mass 1 gravity is negative.
Okay. Let's leave that for now like this. We'll come back to it, but that's basically the dynamics of M1, done and done. What if I go to M2? Do I have Rahimat here able to talk on the mic? That would be a no. Okay. All right. What can I do here? If I want to ask you, okay, I'll ask you some simple questions then. So if I wanted to put a positive direction for analyzing M2 right now, since it's accelerating down, what should that direction be if you can type to us? Up or down? Where should we take the positive to be? Okay, if you take it up right now, you're going against the acceleration. And we have a rule where, again, wherever I see the acceleration point, that's where I take the actual positive. There's reasons behind that choice that are a little bit, long to explain right now. But I've shown you, Jamie, why that is, right? Because, again, you only have one direction of motion here. Basically, the y direction, believe it or not, is this right now. If you take a look at the whole system, this is the positive y direction. It's going like this. So when you set this as plus over here, you basically already tell everybody else what their plus signs are going to be. You tell, for example, the pulley that the plus direction of its spinning is going to be in the clockwise direction, like around like this. And then you tell the other mass that the positive direction of it moving is down. So once you set the plus on one guy, you've set the plus for the others because everybody is connected. You can't go and say right now suddenly that this is going to go up. That would break, the connection between the three objects. Fair enough. Okay. So let's see here. If I want to continue, again, because we can't hear Rahimad, I'll do this one here, and then Jamie, you'll do the pulley. So this one here, what we have, we'll write down Newton's second law statement. So F net y is equal to ma. The mass we're analyzing is m2. The acceleration of it is labeled as a2. And then we're looking at the forces. This is positive, therefore this one's going to be positive now. And the one going up is going to be negative. There we go. So that's the dynamics of that done and done. Okay, and that will give us a second equation here. Fair enough. So the last one here I'm going to give you, Jamie, to do. So let's think. This needs torques. Tell me what the torque Newton's second law looks like.
Net torque equals inertia.
Times
Alpha?
alpha. Okay. The alpha here, we've called it alpha P on the diagram. It's for the pulley. And the moment of inertia, this is supposed to be a thin hoop, right? The inside of it is hollow. So it's supposed to be a thin hoop. The spokes have no mass. What is the moment of inertia of a thin hoop spinning about its center of mass? Do we have that on our list?
I don't remember.
All right, fine. It is mr squared. 1/2 would be if it was a disk.
Yeah.
All right. Now, how many torques are acting on that hoop right now?
2.
And based on our, again, acceleration, positive torque is this way. Which one is trying to spin the wheel clockwise? Think again. We can draw an arrow to prove that if we want. From the center to T2 right now, take a look. This is our R vector. T2 tries to spin this vector which direction right now?
Clockwise.
Clockwise. And that direction is
Positive.
all right. So this is a positive torque from T2. If I go the other way, I hope you can see that T1 here is going to try and spin me counterclockwise, which is negative. So I have to take away the torque from T1. Okay, so far, so good. All right. Now the torque aspect. We got to fill in the size of each of these torques. On our equation sheet, we know that the size can be found by doing this. R is the distance from the pivot point to the position that the force is acting. So for example, if I'm doing T2, the pivot point's in the middle right now, and the force is acting right there where the arrow is pointing. What's that distance?
Distance R.
Capital R. Okay. And what is the force that we're analyzing right now?
T.
Okay, and what is the angle between blue and red vector?
90.
All right. Then we're taking away, we go and visit the other one right now. We go and take away this one. So again, how far is it from the pivot point?
Capital R. Capital R.
The force we're analyzing is T1. And the angle between blue and red vector?
90.
90 again. Okay, so we've got a lot of things under our belt. So that's over. We can cancel a factor of R from both sides. We can call these, again, just 1. That's what they value to. We have here T2 minus T1 remaining equals to MPR times alpha P. That is like your third equation right now. So let's see what the question asks for. And then we're going to use the conversion table over here to see again what we need to solve for. So draw a free body diagram, label the diagram, whatever. This was A, I guess. B, write down an appropriate Newton's second law for each diagram in A. Okay, that's A and B, I guess. Use the equations from B to obtain an expression for the acceleration of the masses M1 and M2 in terms of the parameters M1, M2, MP, and G. Okay, so you see here, they're even hinting you, not that you need really the hint, that A1 is equal to A2 that you've claimed in the beginning, right? So we're aiming to find one of these two guys because it's the same thing. Either you find A1, you have A2. Let's just find A1 then, okay? So wherever I see A2 or AP, whatever other variable for the acceleration, I got to cancel it in terms of A1. Where could that happen? Right here. That is an alpha P. I would like to get rid of it in terms of A1. What do you have to tell me about what I just asked? To get rid of alpha P in terms of A1.
You replace the alpha P with the A1.
A1 over R.
With A1 over R. All right, and if we do that, we have here T2 minus T1. The R's will cancel, right? Because, actually, no, what am I saying? We are dividing. We are dividing. Yes, so the R's are going to cancel, like this R, it's going to cancel with that one as we plug in. So we are remaining here, really, with MP times A1. That's it. Fair enough. And the only other change I gotta make here is call that A1 because they are the same thing. Now, while I'm at it, I could just isolate for T2, bring that there, bring this here, getting myself M2G minus M2A1. I'll call that my second equation. And then I can go upstairs and do the same here, isolate for T1, because I'm planning to plug both of T1 and T2 into the third equation. Okay. You can see I have T1 explicitly in terms of A1. I have T2 explicitly in terms of A1. And then I've got the mixture of these two in terms of A1. All that remains is to mix the equations together, right? So 1 comma 2 goes into 3. We get here T2 is M2G minus M2A1. We're subtracting T1, which is M1A1 plus M1G. We're going to put that in brackets. And this is all supposed to equal MP A1. We have one unknown. We solve. So bring these A1 terms on the other side. This guy over there. And this guy over here. And then collect the G terms together. We have M2G minus M1G. Then MP. We can immediately factor all the masses right now. We can have ourselves here MP plus M1 plus M2 and factor the acceleration A1 outside. So to solve, we're going to have here a division by the entire mass of the system. And then on the top, I'm going to factor G out over here. So it's going to look like M2 minus M1 times G. And that is my answer. I'm not going to do the plugging in the numbers part, obviously, but that is my answer right now for what the acceleration should be. I don't think they can really make this a lot more difficult. Maybe they could put one of the masses on an incline, but even that incline, I don't think they'd give you friction on it. That'd be pretty mean. You never know. Be prepared. But that's how they can make it more difficult. They could put one of these masses sitting on an incline and get it dragged up the incline. Okay, but it doesn't change much, the approach. And we'll probably see a problem like that by the end of the review again. What do we think?
Yeah.
That was a very depressed yes, Jamie.
No, it's good.
All right. Rahimata, you're also following? Let me know in chat. We just solved part C.
Hello?
I can hear you.
Oh, okay.
Are you also good?
I guess.
Okay, we have to meet more for this aspect here because we haven't talked about twerks ever with you alone. Okay, so again, I expect the most comfortable person to be Jamie, a little less comfortable Julie, and very uncomfortable to be Rahimah right now. Okay. In another setup, we have M2 changed so that the acceleration of M1 is 2.2 meters per second squared upwards. Okay, fair enough. How long would it take M1 to come to rest if its initial velocity was again 1 meters downward? Look how they're teasing you here to do kinematics. It's really silly, but whatever. So we have the same system. Okay, I'm going to give it like a silly diagram here. It's not going to be that long of a problem. So we have the little blocks over here, M1, M2, MP, whatever. And we are being told that the mass is being changed for M2 such that M1 goes like this upwards. So M1 is going like this right now, upwards. This is A1. So given is that A1 is 2.2 meters per second squared up. Okay. How long would it take M1 to come to rest if its initial velocity was 1 meter per second downward now? You see, like this is going to counteract your velocity right now, which is going to be going downwards. You're going to be having this kind of V naught. So V naught is 1 meter per second down. And eventually you're going to come to rest. That's the goal here. You want to get 0. This is kinematics. Welcome back. So how do we do this? We have 3 variables out of the 5. We don't have time. We don't have displacement. But we're looking, look what it says. What are we looking for?
Time.
We don't want that. I forget where I've left these, Jamie. I'll try to find them in one shot. Probably, if I look over here, actually, I'm going to find them faster. My high school students, because they use these all the time. But I'll see. Okay, there's like the first version of this, I guess. One sec. I'll get you like the table. The nice little table. So maybe here. Yeah. There you go. Okay. So I'll get you this in your review right there, which is there. All right. So which one are we picking? And why? We don't want to find displacement. We want to find time.
So 2.
So
Number
the
2.
second,
Yep, Rahimot, correct. Number 2. So not a big deal once we get this going. However, you need to use signs here to describe the opposite behavior of these vectors, okay? If you're in 1D, everything's so nice and beautiful, you know, birds are chirping. It's just very calm and peaceful, right? It's not like 2D or 3D where chaos is happening with these vectors. But in 1D, it's like, are you a plus or are you a minus, sir? And you just have to answer that. That's up to you now to determine who's going to be plus, who's going to be minus. It's going to work exactly the same way, no matter who you pick. Now, George's advice. To you, this is a deceleration right now, right? It's slowing you down. So maybe he should be aligned in the negative direction. I know what I said before for the forces, line it up with your positive, but that's doing forces. Here, you're doing kinematics, and this looks like a deceleration. So maybe we should pick the direction of V naught to be the positive. And it's not going to work any differently if like you do it the other way around. But if you have a problem where you have to continue on and do something about the displacement, you might confuse yourself. Like with this being a deceleration and you're calling it positive, you might then plug it in a way to a future equation that messes you up. So I don't know. I just feel like this is a good practice, good habit to think of deceleration as being negative. Okay. So you pick the second equation. It says we're going to turn it into the y component. So VFY is VIY plus AY times time. Fair enough. Now, I'm going to do these are dummy variables. We have to switch them into our diagram variables. What do I want the final velocity to be, Julie?
0.
0. The initial is given as V naught, and the acceleration is A1. So you have 0 equal to V naught. Is this correct, like what I've put over here?
I think so.
No, A1 should be negative.
Maybe freaking out. I love it.
A1 should be negative.
You know, this guy here is not going along this guy. You have to be careful. That's going to be a negative, whatever the number might be. You'd realize it. I'll tell you when that you've made a mistake. Not at that step, but a bit later on. So you have minus A1 times time. Obviously here the time is going to be minus V naught over minus A1. And you can see how the minuses just go away. So you got a very simple expression for how long it's going to take. You would have realized that this needs to be negative when you came over here and you saw that you're getting a negative time. because you don't have the cancellation happen. Okay, so whatever, I can do that really quickly. Maybe we can do it in our head. 1 over 2.2, I can't do in my head though. So it's about 0.45 seconds. 5, let's say 5. It rounds to that. That's how long. So after this amount of time, this is what's happening. Like your pulley M1 was going downwards, it's slowing down, slowing down, and then it's going to go back into the intended direction because it's lighter than M2. It's going to go around the pulley like that. Okay. So what did Jimmy, I've actually, we've spent a lot of time together and I've told you this is something they do all the time. After the forces or torque aspect, they go, why don't we throw a kinematics question at them? Okay, so they do this all the time. Be prepared. And there we go. So that's D, a little bit of kinematics in there. And that's the entire problem. You got, how many marks did we get? 6, 9, 10. We're still not passing. You got a long way to pass because that's question 1. Now I feel like they're going to allow you to pick questions. Hold on. It says attempt all 10 questions. Then again, it is a 2.5-hour exam. So, and I'm not going to be explaining it to you. You're going to be like running through the questions. You're not going to be like sitting and asking questions, right? All right. All of these are terrible profs, but okay. Oh boy, and this is in the recording. I shouldn't have said that. Okay, this is a force problem. I kind of want to skip because I want to look at a topic each time.
I have to go now.
You have to go? Do you want? Hold on, let me pause 1 sec. Let me ask you. So here we go with our good old relative motion. We've got a boat, okay? And its top speed is this much in still water. It wishes to travel to a port which is 50 kilometers away in a direction of 45 degrees. Damn, they're killing you here with the difficulty, but that's okay. There is a 5 kilometer per hour current coming from the west. Okay, coming from the west. They're trying to confuse you there too. Coming from the west, so it's directed where?
East.
Exactly. All right, so let's analyze these. We started with this one. You have the velocity of the current or the water, if you want, with respect to the ground. This is what it's measured when they give you this number. It is 5 kilometers per hour east. And then we have 2 other velocities we need to worry about. We have the boat with respect to the water. We have the boat with respect to the ground. Now, pay close attention because they've done everything they can to confuse you here with which one is this velocity here. You got to really think about this. It says 25 kilometers per hour in still water. So as soon as I turn on the water velocity, you're going to be moving differently. Think about that for a sec. Or even better. When does the water appear still for you? Think about that. If the current is moving at 5 kilometers per hour, let's say, when would the water appear still for you? This is hard, so I'm going to help you a little bit more. Here's the water. It has its own little reference frame. Here's the flag for the reference frame. And here's your questionable boat diagram. And it has its own reference frame. And then we have the ground somewhere over here. So I'm going to ask you this. when does the water appear to be still for you? And I'm going to do this motion and you tell me what you think. Again, when does the water appear still for the boat? When the boat is doing what?
Mm,
It's moving at the same speed as?
The water?
Mm. So what they're giving you here secretly is your velocity that you can do when the water is still. That means right now you're not caring about the current that is going on. You don't care about it. It says in still water, you can do this much. But if the water moves, you're not going to do this much, obviously. So in a way, they're telling you this is the speed you can do, ignoring the speed of the water. Which of the two velocities would care about the speed of the water? Which of these two would care about it?
VBW. VBW.
Mm,
Oh, wow.
ground, because like when someone's watching you from the ground, let's say your engines are closed right now, he's still going to see you move, right? At 5 kilometers per hour east. He's still going to see you move. So the ground reference cares about the water moving, but the water reference does not. The water reference is literally itself. It doesn't care. You're following it. So our velocity with respect to the water is irrelevant of the water speed. You can make this water right now go 200 kilometers an hour, and we won't care when we are asking our velocity with respect to the water, because we've taken this current to go 0. Let me rephrase, because this is complicated. When you ask, what is the velocity of the boat with respect to the water? By default, you assume that this is not as moving with respect to you. You're adopting a frame where you're moving with the water. Versus if you're asking about the ground, you're adopting a frame where the ground is not moving, for example. So if they state in still water, that means your velocity, whichever one of these two is, you have been given a velocity that doesn't care about the water current. The only one that doesn't care out of these two is the one with respect to the water. The one with respect to the ground, you gotta add the current's velocity to figure it out. It cares about the current's velocity. This one does not. So this is secretly VBW. And we're not told, I want to see here, we're not told about the direction. We're only told the magnitude. Okay, fair enough. We don't know VBG at all. It's going to be an unknown. We have some kind of direction here. See, they're encouraging you to even draw a diagram to put in the rest of the given variables. Okay, so they go, okay, we've gotten rid of this part of the problem, and we've gotten rid of this part of the problem. We're just focusing your attention on what we need to analyze still. It says we wish to travel to a port that is 50 kilometers away in a direction of 45 degrees north of east. Now you're thinking, how does this matter? What are we going to do with this info? This here describes your displacement. You have 3 different displacements that we could be talking about: the water with respect to ground, the boat with respect to water. Which one is this one? Let's think. It wishes to travel between 2 ports. The ports belong to the ground. So if there was a guy above, like in an airplane, or someone at a very tall seat that's fixed to the ground, he was watching the boat, he'd look at the boat and he'd see it travel in this direction. Like this is where the port is. This is where the boat is right now. So someone sitting at a very tall chair in the ground would see the boat travel in this direction. That's its displacement vector right now. This is delta D, boat with respect to ground. That's the goal. That's where we want to go with respect to the ground. So obviously, this is related somehow to this. Let's think. Use our noggin up here. We have a displacement, and we want to relate it to a velocity. First of all, should they have the same direction? This velocity and this displacement? I'm going to remind you the definition here of velocity to answer that. What do you think? Should they have the same direction?
Yes.
Yes. They are the same thing off by a constant, which is called time. They are the same vector scaled by a constant. So if this points like this, you can bet that the velocity will point like this too. Now, you've been given the size of this displacement and the direction too. You've been given like a couple of things here. You have this theta, which is 50, I believe, 45. And then you have the size of this displacement as well, 50 kilometers. These are all your givens. All right. Write down the vector equation which describes this situation and define each of the vectors used. Write down all the properties which are known about each vector. By vector equation, Jamie, what do you think they mean by vector equation, first of all?
Is it like what you do to solve the unknown, like the VG equals?
Basically, so you want to express the unknown in terms of these two. Remember the middle subscript cancels, that kind of stuff? Okay, so how would you do that?
VBG equals VBW plus VWG.
Yep, plus VW, comma,
G.
G. And again, these will drop by rule. These will drop and you'll get this velocity back, right?
Yep.
Fair enough. So that literally is A. You get, this is 3 marks. If you remember basically the transformation equation, it's 3 marks. Okay, what about B? Express the vector equation graphically on the coordinate system below. Now, I've only put the displacement here, but I told you this is going to be the direction of the actual the velocity with respect to the ground. So when we go to part B now, and we draw all the velocities, because we're going to do vector addition, I will copy this and I will literally call the red vector VBG, because I told you that they share the same direction. Now we're in the velocity world though. So hold on a second. Where should VWG be pointing on this diagram?
Just east, like, I don't know, east. To
East or to the
the right.
Okay. Now, do they want you to put these head to tail? I don't know, but I'm going to put down the vectors because that's what we are doing. Because I've taught you, you don't have to do the geometry way. Remember, you can just use vectors to do this problem. It's really useful. And that's what we're actually going to end up doing very, very soon. Okay. So express the vector equation graphically on the coordinate system. Find the direction the captain must head in order to arrive at her destination. Fair enough. Okay. I've told you that you can move vectors around. Okay. So if right now this is the outcome, look at this 1 sec. We got to add these two vectors to get this one, and I will color them so you can see them better, but that's what's going on. Okay. Let's say this is yellow. And this one's blue. All right. So we got to add the yellow and the blue to get the red. I haven't put the yellow in though. All right. So first of all, this is going to be a lot smaller. I don't know what I was thinking, making it that big. It's not going to be that big. So it's just a small current. Okay. So we got to add a vector to this. We got to add a vector to this so that we get the red guy. Obviously here then, that's going to be what we need to add. We fill in the triangle. So this plus this gets us the red. Again, the yellow plus the blue gets us the red. Yellow plus blue equals red. Okay. So I think this is what they want to see. Okay, but we're going to use again, we're going to break these down beautifully into components in just a second. Bear with me. This is velocity of boat with respect to water. And this angle is completely unknown. We don't know what phi is. We're eventually going to figure it out though. So that's part B. I would say don't even draw this. I would say just draw this for the answer. That's what they want to see. Okay. So then they go, find the direction the captain must head. So basically solve for the yellow. The full yellow vector, direction and magnitude. That means I must have the red one and the blue one, but I only have the blue one. Okay, he wishes to travel to a port which is 50 kilometers away in a direction of 45 degrees north of east. All right, write down the vector equation, express the vector equation, and then find the direction the captain must head. Okay, this is getting spicy now. I mean that in a bad way, because it's getting more difficult because you don't have the red vector, but you only have the displacement. Okay, write down all the properties that are known. Okay, this is fine. Okay, let me ask you something. Let's say I decided right now, because I'm crazy, I want to find out what this diagram would look in the displacement world. So I'm gonna do a quick flipperoo, turn the velocities into displacements. What would change? So I want to do a quick flipperoo right now and express. I want this diagram, and I want to see delta D's in there. What would change? Remember, do the velocities share the same direction as the displacements? They do. Okay. So what's the difference then? how do I get this?
The time.
And to be fair, while you're traveling from here to your port, the time that it takes to do that motion, the current is going to be acting on you for the same time. And your heading is going to be, you're going to be pointing your boat in that direction for the same amount of time too. All these times are the same. So what's the conversion then? I haven't shown you a problem like this in the past. This is a little more difficult. You just got to multiply all these quantities by t. So, but again, I want to use displacement. Displacement only. Okay, so I'm going to go here and say this is delta dBg. Basically, all these vectors are the same. The headings are the same. Everything is the same when you turn it into the displacement world. But just keep in mind that the displacements are related to the velocities. Okay, we're so far so good. Okay, now from here onwards, we're going to do a breakdown of these vectors. This is your y direction. This is your x direction for us right now. Okay, Jamie, you have more exposure to this. I want you to try and do for me. Let's do the x components together. I want you to see the red vector has an x component right now and a y component. I'm drawing the x one and the y one in right now. Okay. So how would I get this x component of the red vector?
Delta d cosine.
Delta d cosine. Of which angle?
Theta.
Good. And it's positive because it's heading in the direction of positive x. Good. That's the red guy. Now we said, don't forget what we're filling in. 1 second here. Delta d b comma g is equal to, again, the water velocity, delta d water with respect to ground, plus the yellow guy here, which is delta d boat with respect to water. Fine. So you're doing the x component right now of this equation, literally this equation, but the x component of it, like forces breaking down an x and y component. Okay, so on the other side now, the blue, can you get me its x component?
Delta d.
It's literally the whole thing. And then for the yellow, I'm going to have to use this unknown angle, which I'm going to figure out later. But for now, I'm going to have to use that one. 1 second, let me make that a little thinner. I want to put it in here. So I think it's a little too crowded with the lines and all that. It's a little too crowded. So I want you to use the outside for the components only. There we go. Much better. So now we can see the components of yellow better. All right, there we go. Components of yellow. So I want the X one, Jamie. Remember that we're working in the X one?
Same thing, delta d cosine. I don't know how to say, what's that angle called?
Pi. Right. No, totally no offense taken as a Greek. 100% fine with that one. Okay. So I'll put that like that. That's what you have. This is your first equation. Where are the unknowns? Let me point there. And right now, let me think again. Your other unknown is here. Now, again, without confusing you, the delta dWg, all these delta d's are related to time. okay? And we can go and express them in terms of velocity. We've said that a million times. So why don't I actually do this? Let me think about how I'm going to pull this off. That's my displacement. Express the vector equation. They have not given you a time, which is very surprising. So you're going at 25 kilometers an hour in water, in still water, and you wish to go 50 kilometers away in a direction of 45 degrees. So yeah, no talk about time. Okay. So I'll do, I'm still thinking myself how to go about finishing this off. So these are unknowns. Let's talk about the y component. Do you think, Rahimat, you could help me with the y components here of all these vectors? Starting with the red one, for example, like I would like to have this one right now in terms of this and theta. Sometimes I don't know if like the microphone's just muted and she's talking or like she's thinking. So I'm not sure.
Can you repeat that?
So I would like here, Rahimat, this component with respect to the hypotenuse and the angle theta. Think you can do it?
Is it delta D BG sine theta?
Okay. And it's positive because it's going in the positive y. All right, delta D B comma G sine theta positive. All right. What about the blue's y component? Does it have a y component?
No.
No, right? The whole thing is in the x. That's gone. Okay. What about this guy's y component? So we want this. Again, over here, we want this in terms of this and the phi angle. What do you think, Rahimat?
Delta B W, would it be cos?
They're still opposites, the phi to the unknown side.
So sine theta?
Exactly. So sine of phi. And in terms of sine, because it's going up, it's positive. All good then. So this is it for the right-hand side and the y component right now. Okay. Looking good. Looking good. I am interested in that y component. I have, again, two unknowns here. I'm thinking again of how I'm going to go and solve it. Give me a second, because I don't have the time. I'm still troubled because I don't have the time. Okay, what would I do? Well, if it was me in the steering wheel of the exam, I would right now isolate for this immediately. And I'd have it as delta dB comma W cos phi. It's going to be equal to the red guy minus the blue guy. Minus, again, the blue guy. Okay, so I'd call the first one up here equation 1. And I'd call the second one here equation 2. There's two unknowns there and there. I would divide them. So I'd go and take 2 and divide by 1. Immediately you get rid of these. And the sine over cosine becomes a tangent. You get tan of phi. And on the other side, you have this bad boy, delta dBg sine theta, and then divided by this bad boy over here. Delta dBg cos theta minus delta dWg. Okay, and of course you can solve for phi, the heading direction, by taking the tan inverse of both sides. Okay, it's almost good. It looks too good to be true. It's almost there, but you don't know what this is right now, unfortunately. You know everything else. That's 50 kilometers. That is the 45-degree angle, but you don't know what this is, and that's why we needed that time. So give me a sec. I'll even pause the recording for me to see what I can do about that, or if they insinuate something that I didn't catch. Give me a sec. So the issue with the way, again, they've given you the variables is that this needed to happen a bit later. All the relationships, though, that you have here are the same for the velocity. Like, legitimately, you can just copy this. Okay? Go over here, slap this back here, all these equations, and the velocity diagram that you're working from, obviously. Literally, all of the relationships are exactly the same. You just have to turn the V's, the D's into V's, basically. So all of these, turn them into V's. And you get exactly the same stuff. I promise you. And it's because, again, of what I was telling you with the fact that you're going in the same direction. Okay, so we don't need the vector signs at that point. We're doing components. So I'm just going to replace wherever I see this velocity. Literally, it's the same stuff. You would have done it if we worked on the velocity world. You would have done the same things. Okay, so this is going to take a little, like a 30-second, time for me to fix, but we will get it. You'll see why I'm switching back, why I changed my mind. It's because of the way they gave you the variables that allows us to do something clever. Okay, so same equations. Once again, no displacement over here. And then I decided again to divide the two equations, 2 and 1. What would I get instead? Well, again, I don't know VBG. This is an unknown that I have no information on. And that's why I stopped and changed into the displacement world. I don't know V comma G here at all. Okay, I don't know what this is. So why I switched to the displacement world was because I was hoping that I would get some information there to help me about it. I did not, obviously. Now, is there any way to cheat this? Is there any way that we could, let's say, could I figure out what this is if I know what this is?
Well, don't we know VBW?
We do. So is there a way to figure out what VBG is going to be here? Absolutely. But basically, what I could do here is isolate right here for VBG if I want to, in terms of these divided by sine theta. Or I could work on this one too and isolate for what cos theta is going to be if I want to. So basically, I just have to decide here how I want to do the substitution. I know this. I don't know this. I don't know this. I know this, and I know that. Similarly here, don't know, know, and don't know. So it's up to me to decide how I want to go about it. I think what I'm going to do is the following. Let's isolate right now for this one. It's whichever one you want to find first. Honestly, Jamie, they want to find the heading first, though. I don't want to kill the heading. Keep that in mind. If I'm asked for it, I don't want to kill it. So what do I do then? I go and I isolate for VBG here. What's that going to be? VBW divided by sine theta times sine phi. And the only unknown, again, we have an unknown here, an unknown there. Very good. And then I can go above and do the same. Isolate for VBG. Why not? So if I do that, what do I get really quickly? VBG. Take that over there. We got VBW cos phi plus VWG divided by cos of theta. Where are the unknowns? Let me show you. There and there. So what do I do now? I equate 1 and 2 instead. So if I do so, I get rid of VBG for good. And I focus on getting the heading right now. So this guy is going to be equal to this guy. And now we're getting much, much closer. We've got to solve this. Let's see how we can do it. Okay. Let's multiply both sides by cos. We get VW cos phi plus VWG is equal to, you put the cosine over there, you have cos over sine or 1 over tangent. So you get this and then times sine phi. Okay. So this one over here, we want to, again, solve for phi. And so what we can do, let me see it again. We could technically divide both sides by cosine, but then this will get ruined. Give me a sec to think about it here, Jamie. So, okay, it looks like, again, this was a mistake on their part, and it becomes a nonlinear equation that you can solve if you're really adventurous. So let's put the values that we have. VBW is 25. Okay, VBW is 25. Then we have cos of phi. Then VWG is 5. And then VBW over tan theta. Let me do that one real quick. 25 over tangent. Make sure you're in degrees of 45. That is, wow, that's exactly 25. Yeah, because it's tangent of 45 is actually 1. I forgot about that. So this is what you have. I know you get excited here. You think we should factor. Nope, not going to work. You see the 25s and you probably think maybe this is not nonlinear. It is nonlinear. And I can go over here. The best I can do right now is bring everybody on one side. So 25, if this comes there, we have sine phi minus cos phi. And then minus 5 is equal to 0. Call that here f of x or f of phi if you want, and go in Desmos. Okay. So let's see what's going on. We need, again, angles between 0 and 90. If we got something that is greater than 90, we know it's wrong because look at our diagram. Look at our diagram here, how we have the phi settled. It cannot be something right now that is greater than 90 degrees. It needs to be somewhere in the first quadrant. Here we go. All right, tools. Again, the equation is 25 sine minus cosine. 25 sine x minus cos x minus 5. Yeah, I know. I'm not laughing though. They really did this to you, okay? Back in 2013. It's not really funny to me. So there's the root. Again, this root over here is over pi. That's not a root that we want. So that's your root right there, 0.927 radians. All right. So phi is equal to 0.927 radians. You can try it. If you put it in right now, you're going to get 0 for this equation. So let's pretend that this was perfectly fine and totally not linear, and we solved it, all right? For education purposes, what do we do next to find the time? Okay. Well, to find the time, see how it says, how long does it take the ship to reach its destination? Well, we probably need this guy, okay, to get involved right now. Because we know that the length of this is 50 kilometers, but we don't know the time. So we got to find this out. How do we find this out? We have an equation that can take the phi in right there. If you want to call this bad boy equation 3, by all means. And we're going to say that we're putting this back into 2 right now. That's what's going on. So we're putting, wherever we see phi in there, we're putting 0.927 radians. All right, so we got VBW was 25, sine of 45, sine of 0.927. 45 degrees is pi over 4 radians, since we're doing everything in radians. Okay. So VBG will be sine of 0.927 divided by sine, oh my God, I need to be in radians, sine of 0.927 divided by sine of pi over 4 times 25, you get your velocity to be 28. Again, it makes sense. If I'm going to tell you why in a second. This is VBG. So if you want the time, you're just going to rearrange this equation. You're going to get delta displacement, which is the 50 kilometers, divided by the velocity we just found. That's not meters per second. That is kilometers per hour that we've been working on. I need to remember that. And so we have 50 kilometers between the ports and divided by 28.28 kilometers per hour. Therefore, we get that this ordeal should last 1.77 hours. The end. I apologize for that. I'm really sorry about this. This is their fault. I don't think there's a way around it. If there is, I'd let you know in the next session, but that's on them. What happened here is completely their fault. They should have seen this. You gotta love being a TA in these kinds of exams where this happens and then everybody's like, why is this non-linear? I can't solve this. Please, sir, help me. There's like 200 of these hands in desperation. Okay. Fair enough. All right, there's your velocity. There's the time that it takes. There's the heading. Obviously, this is with respect to the east line. And that's it. That's the whole problem. I now regret telling you that the 2013 final was better. It started good. And it's like your typical relationship. It starts good and then it all goes to crap, you know?
Yeah.
There we go. All right. In terms of all that's happened, are you comfortable though, besides the nonlinear thing? Will you be able to break down the vectors here in X and Y components and solve for the unknown that you have in those X and Y components? That's the big deal here. So will you be able to do this on your own and then spot who is the unknown and solve.
Hopefully.
Probably.
Hopefully.
Probably also see another problem like this on the other final, right?
Yeah, there are.
Of course. Okay. So let me see again. Pick and choose here. Let me see again. Let me scroll through and see what's up. I like this one. It's force related. I want to keep the easy ones when the other girls are in here too. I want to do the harder ones with you here. And it looks like this one's pretty good. Switch it up a little bit. We'll do all of these questions, don't you worry, but I'm just picking and choosing tonight.
Can I run to the washroom quickly?
Yeah, let's actually take a quick washroom break. So let's see this one. What are you given? This is going to be actually a lot simpler than what we've done so far. You're given the mass of a child, 25 kgs. You are given that it's spinning on the edge of a merry-go-round whose radius is, well, 2 meters. And the mass of the merry-go-round is 150 kilograms. The angular velocity is 1 rev per second. The child slowly walks to the center. Treat the child as a point particle. The merry-go-round is a uniform disk. Neglect friction on the axle. What is the total initial moment of inertia and angular momentum? They are driving you to do these things first. Fair enough. So we go back to our template and we understand we're going to be spinning this. I'm going to look at this from a top view again. It makes more, it will show more details if you do it this way. So the center is here. We are spinning about the center. Okay. And we're going to find the girl, I think she's on the edge in the beginning. So she's somewhere over here, maybe like her center of mass is like there. The disk center of mass is there. Fair enough. She weighs MC. Why MC though? Oh, because it's a child. Okay. And we have them spinning again. I'm going to put the omega over here like that. This is like omega 1 because we are in the beginning, frame 1. That's what I'm going to call it here too. Fair enough. Okay. So for the disk right now on its own, look again what's going on. If I was to use the parallel axis theorem for the disk, I would be looking for the center of mass moment of inertia plus this term. But the thing is, you're spinning about an axis right now that is literally centered. It's literally on your center of mass. So that distance here is what?
R.
That would mean that you're spinning about somewhere over here, like you're spinning that disk like this.
0.
0. We don't need to use the parallel axis theorem for that one. And if this is a disk, we have a list of moments of inertia. This one is mass times its radius squared divided by 2. mr squared over 2 for a disk. Fair enough. And then for the point particle, which is the child, I do the same. So I center of mass C. So then again, this would be md squared. Now, if it's a point particle, spinning a point particle about its center of mass, no resistance. Therefore, this is
0.
how far from the rotation axis is the child?
R.
Right. Okay. So what are we going to put for this distance again? Instead of spinning the child about its center of mass, we're spinning it about here. How far away is that
RM.
RM? Okay, so we have, there we go. So RM squared. All right. So this ends up being M child RM squared. And this ends up being M merry-go-round RM squared over 2. So we're going to define a quantity that says the total is the child plus the merry-go-round. I said I disk. I guess this is I merry-go-round. Okay, so the total again is the sum of these two. Not a big deal. And we can probably find these as numbers if we were asked to do so. You were asked to do so. I'm not going to do it here. We avoid numbers like the plague. But you can, this is determinable right now. This is done. So everybody in the beginning is spinning at this velocity. You have two options for angular momentum. Here they come. Which one am I choosing?
Oh my God.
Again, if the child and the disk are spinning at omega 1, what do I put as L1?
I total omega 1.
I total omega 1. You are pre-assuming here that the direction is positive this way, just mentioning. That's it. That answers, I think, question A. All right. Total initial moment of inertia and angular momentum, done and done. What is the final moment of inertia and the final angular momentum? Okay, so we take this and we go now to frame 2. Something's changed in frame 2. Let's take a look. So it says the child slowly walks to the center. So she is now here. Okay. So what has changed if she's walked all the way to the center right now?
The moment of inertia.
What would it be for the child now?
Would it also be 0?
Because now for the child, the distance of its center of mass from the rotation axis, it would be 0 over here. That quantity here would be 0. So we get no contribution from the child, but the moment of inertia of the disk hasn't changed. I mean, we didn't do anything to the disk. So it's still its mass times its radius squared over 2. Perfect. Now, if the child walked toward the center, obviously we've changed the angular velocity here to be something else. Is it faster? Yes, because we've reduced the moment of inertia. So in order to compensate for the angular momentum, if the moment of inertia dips, the omega climbs. You don't need to indicate that on the diagram, but it's nice to know again. So what is L2 now? The final angular momentum.
I am omega 2.
Right. So it's really I total, but the child does not contribute this time. And we get just the product of these two. So what do we do for conservation of angular momentum?
Set them equal to each other.
So we got I total omega 1 equals to IM omega 2, and we can easily figure out what omega 2 is. There we go. So again, it depends if you want to open up what the I total is. It doesn't really matter right now, but I'll put it in terms of original variables. This is m child rm squared plus mm rm squared over 2 divided by rm squared over 2 times omega 1. This is in terms of original variables. That's it. If you wanted to find omega 2, which is probably what they're asking for, there you go. So that's part C. And then they go, what are the total initial and final kinetic energies? Okay. So for D, how do we express rotational kinetic energy, Jamie?
Inertia omega squared over 2.
Uh-huh. So in the beginning, we have both of them moving at omega 1. How would you describe the total kinetic energy of the system?
Inertia total omega 1 squared over 2.
Good. And what about the final? What's going on there?
So it would be inertia m omega 2 squared over 2.
Right. Still the total again, but child doesn't contribute. Okay, here we go. If we want to find the ratio, do we want to find the ratio? What are we doing here? Is kinetic energy conserved? Why or why not? What do you think? Are these going to be exactly the same?
No.
What is a reason why they're not the same?
They have different moments of inertia.
Okay.
I don't know.
You must have lost some energy somewhere or gained some. So the child's walking toward the center. The child itself, through its metabolism, if you want, as it's walking, right, it's spending some energy to counteract, the tendency of the merry-go-round to spin it around. So it's adding, in a way, kinetic energy to the system, believe it or not. It's adding in a way. It's making it spin faster. So again, we're gonna see here, there's gonna be a difference between these two. And whatever the difference is whatever was wasted, again, by friction as the child is moving from edge to center. So I've put them in right now like this. I don't really want to go and express them in terms of original variables. You get the point. By now, you would know this as a number. You have this as a number. You'd know this as a number, and you'd have that as a number, omega 2 here already. So you just plug in and evaluate. So I don't want to like express them into original variables, right? But that's all you have to do here. So yeah, there's a little bit of friction that's acting because, again, if, let's say right now, you had a frictionless merry-go-round, okay? And again, this is like frictionless, and you tried to go as the child from here to the center, you wouldn't even be able to do that, okay? You wouldn't even be able to do that. You'd put a force to push yourself forward right now, but there is no way you would be able to do that. There is absolutely no way. You'd be walking in place. You'd be just walking in place as the merry-go-round spins under you. You'd be going nowhere. So it's friction again that does its miracles here to get you to the center. Okay, not too bad though, right? Very standard problem
Yeah.
in A momentum. All right. Do you want to do one more or call it here for tonight? We have several sessions coming up. Don't worry, there's plenty next week.
Okay. I kind of like, I think it was the 2014 like midterm one.
Or final?
Yeah. Oh yeah. It was like it's a midterm. It's not a final, but it had another like relative motion one. that
I'll look at that one.
Mm, yes. That
This one.
That yeah. I don't know. These kind of confuse me a little bit.
You see why. Sometimes it's not even your fault. Okay. A compass mounted on the deck of a boat indicates that the boat is pointed in a direction 30 east, 35 south. That is, again, your heading. And that is going to be the direction of your VBW, not VBG.
Yeah.
So, like, think about it this way. You know, you have north, east, let's say over here, and your boat, you have directed it right now like this, okay? That is your pointing with respect to the, again, the water. But with respect to the ground, someone, if you have water right now that's moving this way, they would see you move this way. You see what I'm saying? So even though you're pointing your boat in the yellow direction, someone from the ground is seeing you move in the red direction because of the water. So the compass obviously is measuring the yellow here. Okay, so we're going to say here, let's keep that in mind. However, the satellite navigation system indicates that it's actually going, look, 25 degrees. Again, on my diagram, how does this reflect? Okay, so we got here, east of south. East of south. Couldn't it be in the first quadrant? That'd be lovely, but no. Okay, so the yellow velocity from the previous problem is the 35-degree one. VBW is the 35 degrees east of south. And then the satellite navigation system says, no, you're going 25 degrees east of south. Isn't that how you read it, Jamie? Just again, because
Yeah.
I forget, east of south, not south of east right now.
Yeah. East of south. I'm pretty sure.
Okay. Because you've seen this every day in the course. I have not. We never talk about headings like this in upper year physics, but whatever. So east 25 of south, we got it to be over here. Okay, so that's 25. And this is VBG, because the satellite is tracking what you're doing with respect to the earth, the ground. Okay. If the water current is flowing in a direction east 40 north, so 40 degrees east and north. And there we go again. 40 degrees east and north. V water ground. 40 degrees east and north. What is the magnitude of the velocity of the water current relative to the shore? So we're looking for VWG actually. All right. So before we jump in, put down what we know again. So given, says the boat is pointed in a direction this much. We are not given the velocity of the boat with respect to the water, but we are given the velocity of the boat with respect to the ground. So again, V boat ground is 50 kilometers an hour. V boat water is unknown. And so is VWG. Okay, but all the angles are known, so don't worry. We still have two unknowns and two equations that we're going to build. Okay, so this is the yellow one. We're good to go. So, Jamie, we want to break these again into X and Y components. Get ready to do this. Here's the water velocity broken into components. The yellow one over here. Of course, it's in the way. There we go. All right, and then the red one. Beautiful. So with the plus y being upstairs and the plus x being like this, we want to find those components. Now be careful. Look what angles they've given you. They've given you this 35 is the angle that the yellow one makes. I'm just going to help you out a little bit. And this is the angle that the red one makes with respect to the negative y-axis. This one's the blue. So if that's a 35 there, you can make it jump into the triangle by alternate angle. Yeah, alternate angle theorem here like this. That's going to be 35. And similarly, alternate angles again, that's going to be 25. Similarly, again over here, alternate angles, that's going to be 40. Okay, so I've got you angles in the triangles. All you have to do is do the components right now. But before we jump even into the components, got to remember what you're building. VBG, this annoying equation again, is equal to the water velocity with respect to the ground. Actually, we'd put first the yellow one. V boat water plus V water ground. Fair enough. So you want the X components right now of all of these. Let's get it.
So it would be V B G. Wait. Yeah, sine.
Opposite, so yeah, sine.
25.
Okay.
And then VBW sine 25. And
25?
oh, no, 35, sorry. And VWG sine 40 plus.
Okay, so VWG sine 40. Let me check them. That's good. And the others are good too. Okay, and they're all positive because they're all pointing again to the right. All of these components are pointing to the right. If not, they would have been negative. So pay close attention to what I just said. If not, they would be negative.
Yep.
Okay, do the y's.
Okay. Yeah. Wait, what? Okay, so would it be negative? VBG cos 25.
Mm-hmm.
Well, negative VBW cos 35 plus VWG cos 40.
Okay, so plus VWG cos 40. I'm just checking. You're good. Okay, all good. Unknowns again. We don't have the yellow and the blue. Nothing on the yellow and the blue right now. So this one and that one. This one and that one. Again, in my opinion, I would probably just eliminate one of these pairs, either this one or that one, depending on who you want first. But let's see who they're asking for before we make a move. What is the magnitude of VWG? So I don't want to kill VWG. I want to preserve it. I'm going to kill these two guys. How am I going to do it? By isolating for VBW right now. So VBW sine 35 is going to be equal to, just take everybody on the other side. VBG sine 25 minus VWG sine 40. And the same over here. Isolate this one by taking it there and bringing this one here. VBW cos 35 is VBG cos 25 plus the blue one. Okay, so these are equation 1 and 2. Here's one of your unknowns. Here's the other one. What you can do again, I love dividing them. So I'm going to go ahead and divide 1 by 2 so I can create a tangent for the angle. If I divide 1 by 2, these go bye-bye. And then I have sine over cosine, which gives me a tangent. Tan 35, and then this is equal to this side, which I'm too lazy, so I'm just going to copy it. It's this side over here divided by this side over here. Again, the only unknown being here and here. We're going to cross multiply here and try to solve. That's all that's left. Okay, we can do it real quick. Let's see. VBG cos 25 tan 35 plus VWG cos 40 tan 35 is equal to VBG sine 25 minus VWG sine 40. Highlight the unknowns, bring them together. So I'm going to do this moving there and this moving here. Immediately factor VWG. So we have cos 40 times tan 35 plus sine of 40. I'm going to quickly evaluate this right now. I'm too tired of carrying this around. Cos, make sure you're in degrees. 40 times tangent of 35 plus sine of 40 is around 1.179. All right, and on the other side, we're going to factor VBG. So we're going to factor this VBG, and we're going to have sine of 25 minus this guy. So minus cos 25, and then tan 35. Again, this is going to be sine of 25 minus, I have to do, hold on, and let's do the product first. Cos 25 times tan 35 times -1 plus sine of 25. All right, so this is negative 0.212. All right. So VWG is negative 0.212 divided by 1.179 times VBG. Okay, let me make sure everything is good with the signs. I haven't screwed up anything. We're good. Move this on the other side, factored it. Okay, looking good. And the VWG on the first side. So that's also good. That looks good. Okay. As for the signs here, you got them all right. Just give me a sec just to check them, So the Y1, red has a negative Y component, goes 25. Same with the yellow, goes 35, and then we have a plus, goes 40. We rearranged for the yellow. Okay. Yeah, that's good. That's good. And then the other one here, all positives. Yep, and then rearranged for the yellow again. So we took away the blue. Absolutely. We copied them correctly. I checked this, it was fine. All right, I'm just a little troubled why I'm getting a negative here. There is a real chance that they are not reading these headings the way we do. So you know how I said 35 east to south? There's a real chance they're reading it as south of east. That could explain the discrepancy, but if we don't get the same number, it really means we're reading these wrong. So anyways, VBG, we said is going to be 50. We have 0.212 divided by 1.179 times 50, get around 9 kilometers an hour, and it's a negative 2. And if it's not on the options, we're reading this the opposite.
It is.
There's a 9, yeah, that I got E here.
Yeah, that's the right one.
Do we know if it's the right one?
Yeah, I have like the way they did it with all the angles. Like they found all the angles and then did sine law.
Oh, so geometry basically.
Yeah, but
Okay.
I like doing it.
That's not a big deal if they did it that way.
Mhm.
I'm still not liking that negative. Give me a sec. I really don't like the negative, even though it's correct. One sec. Recording. Let me put that on the recording as well. Okay, so apparently the reason why we have a negative is that this is red 35 south of east. I don't know why this convention, it confuses everybody, including me, south and then of east, where a normal person would read that as east to south. But you know, it's the opposite, it's south of east. So we're getting the correct magnitude and what we did here, getting the correct size, but the sign here makes no sense because we've read the angles opposite. Anyways, so you'd still get, if we read it the right way, we'd still get 9 kilometers per hour, but it would be positive now. It's just that we've read them the wrong way. Good to have on the recording too. Anything else before we go for tonight, Jamie?
I think that's good for tonight. Yeah.
Okay, we'll come back and hit this again very soon. We're probably gonna do the entire 2013 and 2014. Okay. I'll stop the recording here.